diamagnetic material in this section. Let me explain the diamagnetic material with a representation. Suppose in a region there exists magnetic field like this. You see this clearly. Here lines of force are close to each other. Here lines of force are away from each other. That means this region is a stronger magnetic field region and this is a weaker part of the region. This is a stronger part, this is a weaker part. Suppose if you keep any material here, if this material goes from stronger part of the field to the weaker part of the field, then this material is a diamagnetic material. Why is it so? Suppose there exists a uniform magnetic field. Let's say like this, the lines of force are parallel to each other. Now if you keep a diamagnetic material, this diamagnetic material will develop magnetism in a direction opposite to the external magnetic field, because we know that susceptibility of the diamagnet is less than 1. The susceptibility is actually less than or equal to -1 or less than 0. It is always less than 1. Because susceptibility is less than 1, its magnetism is opposite to the external field, so it will exclude the lines of force from here. That means the magnetic field previously was like this. Now the magnetic field will try to go around the magnet because this magnetism is in the opposite direction. But only a few lines manage to go through this. Only a few lines. It is of the order of 10 power 5:1. For every 1 lakh lines of force, 1 or 2 lines of force will be excluded in a normal diamagnetic material, because most of the diamagnetic materials are weaker diamagnetic materials. Because chi value is between -1 to 0, we know that chi value equal to mu r minus 1, which means that mu r is equal to 1 plus chi. Then mu r value, so the less value means 1 plus chi value. Chi value is -1. 1 plus -1 becomes 0. It is less than or equal to 0 and less than. Chi value is 0. Substitute chi value, maximum chi value here. The minimum chi value here. So what is mu r minimum? Mu r minimum is equal to 1 plus chi minimum. Chi minimum value is -1. 1 minus 1 is equal to 0. What is mu r maximum value of chi? And mu r is equal to 1 plus maximum value of chi. The maximum value of chi is 0. So 1 plus 0 is 1. So the range of this is relative permeability. The relative permeability of a diamagnet is from 0 to 1. For the magnetic susceptibility is from -1 to 0. Because mu r is less than 1, we know that mu, permeability of the medium, is mu naught times mu r. Because mu r is negative, this whole value is negative, hence mu will be less than mu naught. So permeability of the diamagnetic material is less than permeability of vacuum. So the thing is, why it is negative? See, when an electron moves around a nucleus, it possesses angular momentum. That means that it moves around the nucleus in an orbit. When this moves around the nucleus in an orbit, it produces tiny electric current, circular electric current. Because of that, a magnetic field is produced. In a diamagnetic material, the net magnetic field of an atom is 0. Then net magnetic moment of an atom is 0. Of an atom equal to 0. So when that means that if there is an upspin for the electron, for the upspin magnetic field is upward, means for the downspin the magnetic moment will be in the downward direction. When applied to external magnetic field, the one in the direction of the external magnetic field will be reduced, because according to Lenz's law. Hence the magnetism in the direction of the external field gets reduced. So magnetism of the diamagnet in the direction along the external field is decreased or is diminishing external field decreases and the one opposite to the direction of the external field increases according to Lenz's law. That is why diamagnetic materials develop magnetization in the opposite direction. And the other important part in this, some of the important diamagnetic materials are bismuth, copper, lead, silicon and nitrogen. So these are at standard temperature and pressure. These are all diamagnetic materials. Bismuth, copper, lead, silicon and nitrogen gas are all diamagnetic materials at standard temperature and pressure. So even this one nitrogen at standard temperature and pressure I'm mentioning, even water and sodium chloride, are diamagnetic materials. So diamagnetism is present in all substances, but the diamagnetism is very weak. Even though diamagnetism, that property is present in almost all substances, they are weak in nature. So the other part, the most important part is I am going to talk about superconductor. Superconductor is a perfect diamagnet. What do I mean by that? See, generally when a conductor becomes superconductor, you take a normal conductor and you keep decreasing the temperature of the conductor very low. At one temperature, this normal conductor becomes superconductor. That temperature is called critical temperature. Okay, so materials, okay, at a particular temperature, when you keep on cooling the materials at a particular temperature, material becomes a superconductor. A superconductor is a perfect diamagnet. Let us have this thing. This is a normal conductor, and before critical temperature, let us say lines of force are going like this, and the moment the temperature is below the critical temperature, it becomes a perfect diamagnet. Almost no lines of force will be going through this material because it is a superconductor and it is a perfect diamagnet. The relative permeability and of a superconductor is 0 because chi value of a superconductor is -1. So this is an ideal diamagnet. Superconductor is a perfect or ideal diamagnet whose relative permeability is 0 and susceptibility is exactly -1. This exclusion of the magnetic lines of force from the material below critical temperature is called Meissner effect. Meissner effect is named after the scientist who discovered this. So this is above critical temperature. This is the temperature above critical temperature. Lines of force are passing through the material. Below critical temperature, this conductor becomes superconductor. Hence, none of the magnetic lines of force are going through the material.